Okay, welcome to the programming languages final exam review for fall 2024. This exam will cover chapters or lectures 6 to 9. First lecture is on syntax and will cover regular languages and context-free languages and a few things that you can do with them. So let's first define what a language is before we get to this. Let's start with the alphabet. Now, what's an alphabet? It's a set of symbols, okay? Let's say your symbols are A, B, and C. This is an alphabet. It's just a set of symbols or characters, if you want to call them by that, okay? Now, a string in this context is a series of symbols one after the other. So let's say A is a string of length 1, B, A, B is another string, and this one has length 3, C, B, A, C, A is another string. Anyways, there's infinitely many, as you can imagine, of all kinds of lengths. You can also have strings that are of length 0, okay? Which means they have no symbols in them. And usually this is denoted by epsilon, okay? This is a string of length 0, and like even though it's denoted by a symbol epsilon, this is not actually a symbol. It's just a way to denote, you know, the empty string that has nothing in it, okay? Now, if we take these all together into a set, now this is a language. A language is a set of strings. That's all it is, okay? So this is the language that contains the empty string, the string A, the string BAB, and the string CBACA. That's what a language is. It's just a set of strings. Okay? Now, there's all sorts of languages, and they're usually classified in what's called the Chomsky hierarchy. And at the lowest level, well, you have finite languages, such as this one, with a finite number of elements, but you also have, of that, regular languages, which can be specified by regular expressions. So, regular languages may or may not be infinite, but point is that because they might be infinite, there's no good way of like you can't really list all of those infinitely many strings, right? So what you do here is you specify a kind of rule set for determining whether a string is or isn't in the language, okay? And in a finite amount of time. So given a string and a regular expression, you're going to be able to use the regular expression to determine whether or not the string is in that language, okay? In the language corresponding to that regular expression. And this is the key thing, because since these languages might be infinite and you can't list out all the elements, you have to have some kind of way of determining whether a string is or isn't in the language, right? A kind of decision procedure, if you will. So that's what regular languages are good for. Within like a few symbols, a few characters, you can specify a language. Okay. Now, following up from the discussion on strings that we had, X and Y here are strings over the alphabet. One second. Over the alphabet 0, 1. Okay. So this is your set of symbols. You can only use 0 and 1. And here are two strings. The first one is 0, 1, 0, and the second one is 1, 1, 0, 1. Now, you can concatenate strings, which means you put one after the other. So XY First you put all the symbols from X, so 0, 1, 0, in the same order, of course. And then you put all the symbols in Y in the same order that they came originally, okay? So 1, 1, 0, 1. The string XY is 0, 1, 0, 1, 1, 0, 1. So seven symbols in the string, okay? Now, concatenation of languages, i.e. concatenation of sets of strings, works the same way, except that you do it with all of the possible combinations of strings from the two languages, okay? So you have a language L1 and L2. And what you do here is that their concatenation, L1, L2, is the set of all concatenations of strings X and Y, like XY, first X then Y, where X is in L1 and Y is in L2. That means you take a string from L1 and you concatenate it with a string from L2. And you do that for every possible combination of string from L1 and string from L2, okay? So suppose you have L1 equal to 0, 1 and 0, 0. So that's two strings. And L2 is 1, 1 and 0, 1, 0. The concatenation of L1, L2 is the set of all possible concatenations of two strings where the first string is from L1 and the second string is from L2, right? So here's the first string, which is 0, 1 with 1, 1. So that gives you 0, 1, 1, 1. The next string is 0, 1, 0, 1, 0, which you got from 0, 1 and 0, 1, 0. The next string is 0, 0, 1, 1, which is 0, 0 concatenated with 1, 1. And the last string is 0, 0, 0, 1, 0, which is 0, 0 with 0, 1, 0, right? So that's the concatenation of languages. And finally, we have the union of languages, which is just take all the strings from both languages and put them together into a new language, okay? So you have L1 equal to 0, 1 and 0, 0 again. L2 is 0, 1, 1, 1 and 0, 1, 0, okay? Notice the repetition here. 0, 1 is in both languages. However, in the union, it only appears once because sets don't accept duplicates. Although I'm sure you know this from discrete math or something, so I'm not sure. I don't think it's really a concern. Anyways, like I don't need to emphasize it. Anyways, yeah. So the union is the set of all strings that are in at least one of the two languages. So 0, 1's in both, that counts. 0, 0 is in one of them, that counts. So it's in the language, in the union. 1, 1's at least in one of them, which is L2 in this case. So it's in the union and so on. Now, we just learned concatenation of languages. So all concatenations of two strings where the first string is from the first language and the second string is from the second language, right? Now, what about concatenating a language with itself? This has a special notation which is similar to powers. Okay, and what happens here is that L0 is the empty, the string containing only the empty language. So, oh my god, the language containing only the empty string. I'm sorry. Okay. And then L1 or just L is, the language itself and nothing else. Then L2 would be the concatenation of L with itself. So remember, this is a language, so you can get a lot more strings out of this, possibly. So if we had 0, 1, 0, 0, the concatenation of L1 with itself over here is 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 0, 1, and 0, 0, 0, 0, right? So that's 4 strings, although it's not necessarily in powers. Anyways, So L squared is LL, L cubed is L, L squared, or L squared L, same thing, and so on, okay? So this is a recursive definition where L to the ith power is the concatenation of L with L to the I minus 1 power, okay? And the base case is L to the 0 being the language containing only the empty string. Next, we have the Kleene closure, which is the union of all powers of the language, okay? So the notation here isn't really correct. This is the correct notation. So we know language concatenation, we know language unions. Now, the star here is defined in this way, okay? The union of L0 with L1, with L2, with L3, with L4, and so on, okay? And that's basically it. So this is just, you know, the language containing only the empty string, and then this one would be 0, 1, and 0, 0, right? And then this one would be 0, 1, 0, 1, sorry, 0, 1, 0, 1, 0, 1, 0, 0. I need to get like a drawing tablet or something. 0, 0, 0, 1, and 0, 0, 0, 0. Okay, so you have 7 strings in this part, but you also have L3, which has 8 strings, and L4, which would have 16 strings in this case, right? So take the union of all those infinitely many powers of L. So yes, the star is an infinite language, okay? What else? The positive closure, it's defined in the same way, except you don't count L0. So you need at least one copy, kind of a string from L, okay? But the positive closure isn't really emphasized too much in this lecture, so don't worry about it too much. Let's move on. So a regular expression, it's defined in this way. First, we have the base case, which is 3 different base cases. You have the empty set, or the empty language. You have the language containing the empty string, and you have the singleton language, which consists of a single, uh, single string with a single symbol. Okay, so this is kind of a notation. Even though these look like symbols, even though A looks like a symbol, it's actually a language. Okay, so that would be kind of confusing, but just bear with me for a second. So these are the 3 possible base cases, right? Now, keep in mind that we're dealing with an alphabet here, so sigma might have, I'm just not gonna draw the braces, A, or the commas, A, B, C, okay? So this is your set, A, B, C. So you'd have, what the hell is that? Okay. You would have phi, epsilon, A, B, C. And these are your base cases for the regular expression, okay? So all of these are regular expressions by definition. Okay? Next, you have, now given 2 regular expressions, let's say R and S, you have 4 things here. The first one is R plus S, which is the union of the set corresponding to the regular expression R and the set uh, corresponding to the regular expression S. Okay. So for R plus S, let's say our regular expression R is actually A and the S here is B. A plus B is the union of the set or of the language corresponding to this with the language corresponding to this. So remember, the regular expression here, A, represents the language containing the string A. Okay? So in reality, this is this language union with this language. Okay? And that gives us, uh, A, comma, B. This is the set or the language corresponding to this regular expression. Okay? Now, it's important to note that R plus S here is also a regular expression. Okay? So you can do something like R plus S plus, let's say, another regular expression, T. Okay? This is completely valid because this itself is a regular expression. So this can be like U plus T, which is in the form R plus S, right? So it's a regular expression. Anyways, RS. Now, this is the concatenation of two languages. So your first language is R, which may be a regular expression that corresponds to a language with multiple elements, or it can be just one, or even zero with the phi, although that's not usually the case. You can have the Kleene closure, which is, L star for some language L. And finally, the grouping. Now, this is just the same thing as that, except, the whole thing is taken as a single thing. So let's say the concatenation of R with S plus T. Okay. So first you do this, which is the union of the of the two regular expressions, or the two languages corresponding to these regular expressions, S and T, and you concatenate that with R from the beginning, or whatever strings might be in the regular language corresponding to R. Okay. So let's do some examples. Suppose your alphabet is 0, 1. First, this is the set containing only the string 0. 1 is the language containing only the string 1. Now, when you do plus here, you're doing a union. So the result of the 0 plus 1 is 0, comma 1. Okay? Now, the star here, now first you have the grouping, obviously, and the star applies to the entire group 0, 0 plus 1. Now, the star has the, let's say, the union of all possible like powers of this language 0, 1, right? So let's say this is L, then L0 would be just the empty string, right? And then L1 would be 0, 1. L2 would be 0, 0, 0, 1, 1, 0, 1, 1. L3 would be the 8 strings in of length 3 in binary, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, that's 8 strings. Union all of those together, also with L4, L5, L6, all the way up to infinity, and that's your language. Now, key thing you need to develop here is the ability to understand what the regular expression is telling you, right? So, if you want to try to understand this, The star is intuitively kind of, it's letting you go back and choose something again, okay? So let's say you're walking into this regular expression from the left. Now you have 0 plus 1. You pick one of them. Can be 0, can be 1. Let's say you pick 0. And then you encounter the star. You go back to the beginning of whatever it applies to, which is the beginning of this group, the left parenthesis. And then you pick something again, okay? Let's say you pick 1 this time. So your string is now 0, 1. And then you continue with the star. You can go back as many times as you like, or you can even not go back at all, okay? And in fact, the star also lets you skip this entirely because it's a concatenation also with L0, which is the string containing only the empty, the language containing only the empty string, right? So if you want to have like a list of all of these strings described by this regular expression, it's the empty string 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, and so on. That's all strings of zeros and ones. I hope it's clear, but like if you need the explanation, then uh yeah. Anyways, next 0, 1 star. So first we start with the 0, and you cannot skip this because the star only applies to the 1 here, not to the 0. Okay? So you have the 0, and then you have the 1 star. Now the 1 star, you can have no ones at all. You can have a single one, you can have like 5 ones, 100 ones, that's totally fine. So this language consists of the string 0, 0, 1, that looks like 61, 0, 0, 1, 0, 0, 0, 1, and so on. Okay? Next. You recognize this from here, 0 plus 1 all star. And this says all strings of zeros and ones, right? Now, the concatenation here with 0 adds a kind of restriction where the string begins with a 0, but after the 0 you can choose whatever you want. Okay? Okay, moving on to this example. You have 0 plus 1 star followed by a 1. Now, 0 plus 1 star, as we just mentioned multiple times, it's all strings of zeros and ones, any possible sequence of zeros and ones in whatever order you like. And the only difference here is that there's a 1 at the end. And this means that no matter what you generated by this, you cannot avoid also generating a 1 right after it. Okay? And this means that this is the language of all strings of zeros and ones that end with 1. Next is this example, 0 plus 1 star, 0, 0 plus 1 star. Now, with this one, you have a part that generates literally anything, another part that generates anything, and you have the 0 right here, okay? And since it's a concatenation, it adds a kind of restriction where there needs to be a 0 somewhere in the string, okay? So it doesn't matter whether it's the start, which you can do by just not generating anything. Thanks to the star, you can generate nothing at all, okay? Or can also appear at the end if you do the same with this one. By using the star, you can choose not to generate anything. But anyways, point is, there needs to be at least 1 0 because of this concatenation. Next, this example is basically the same thing, just extended to have 2 zeros instead. The first one's right here, and the second one's right here. And in between them, you can have anything, okay? Now, this expression is relatively easy to understand because these parts say literally anything, and then they're concatenated with two zeros right here. So it's very clear what this is saying, that this is saying that you have at least two zeros somewhere in the string. Okay. Now the same language uh, is given by this regular expression. So you can have multiple regular expressions that describe the same language. However, this one's a little more interesting in a way. So what happens here is that no matter how many zeros you generate, um, no matter how many zeros are in the string, there is going to be kind of the last two zeros, right? And between those last two zeros, you can't have zeros because, well, they're not the last two anymore, right? So this is the second last zero and this is the last zero. Now, if the part between them had any zeros, then this is no longer the second last zero, right? So yeah, that's kind of the cool thing about this regular expression. And it kind of specifies like, hey, these are the last two zeros. So in between them, there cannot be a zero. However, what's before that, you can have anything you like, okay? So whether it's like a million zeros interspersed with some ones, it's completely up to you. Just the point is that there's at least two zeros, and among them, the last two, well, they don't have any zeros between them because then they're not the last two zeros anymore. I'm not sure if I explained that properly. It's kind of weird, but I hope you got the point. Next one is the set of all strings of zeros and ones that contain an even number of zeros. Okay? Now you can have 0 zeros, you can have 2, 4, 6, 8, 10, 12 zeros, however many, just as long as it's an even number. Okay? Now, what this part says is whenever you generate a zero, you're gonna have to generate another corresponding zero at some point, okay? In between them, yes, you can have many ones, just as the point is that at some point there has to be a zero. And that's why this is 0, 1 star 0. Or you can choose not to generate any zeros at all, in this case, totally valid. And that's why there's a 1 here. So, this is all strings containing an even number of zeros. And remember that the plain star here lets you go back and choose again. You can loop over and over, choose whether to generate a 1 or a 0, 1 star 0. And if you go for this, then you're adding two more zeros to the string, okay? Next up is another regular expression that describes the same language. You can start the string with ones, you can end the string with ones, that's something. And in between the two zeros, you can have any number of ones, so that's also something to consider, kind of. And similarly, if you flip the same regular expression, you get this one, which, believe it or not, generates the same language. Finally, we already covered this one, but this is another way of kind of interpreting it, representing the same language. Here's some identities, stuff relating to like the algebra of regular expressions. So the empty language concatenated with a regular expression from the left or the right gives you the empty language. So yeah, so that's multiplying by 0. Similarly with the uh, the language containing the empty string. It's like multiplying by 1 in that you concatenate from left or right, you get the same thing. Now, the empty language star gives you epsilon, and the reason is because it's raised to the power of 0 here, and by definition, that's always equal to the language containing epsilon, right? Second. Okay. Now, this is just the concatenation repeatedly of epsilons. No matter what, you're always just gonna get, well, epsilon, because it's the empty string. 0 plus 0 is 0, okay? Next. For unions, this is, what's it? It says commutative because this is basically choosing either U or V, and that's the same thing as choosing either V or U. So that's kind of clear, I hope. This is just U, this is just U. Now this is kind of important or kind of surprising to some, in that if you repeat the Kleene star, you just get the same thing, okay? Like a single star. In addition, I think we covered this earlier, but concatenation distributes over union. So U into V plus W gives you UV plus UW, believe it or not. And if you flip the order, that's also true. But you need to keep in mind that UV is not usually equal to VU, okay? Unless U and V are the same, in which case, yeah, obviously. But otherwise, no, not necessarily. UV star U is the same as UVU star. And we saw this, I believe, in, yeah, right here, okay? So that concludes the part on regular expressions and regular languages. I'm gonna stop the recording here so that I can start a new one afresh. So yeah, that concludes this part of the lecture. 11 slides. Okay. So moving on to context-free languages, which are kind of more general than regular languages, which we just covered. Yeah. So, well, not all languages are regular. An example, a classic example is this language, which has some number of A's followed by the same number of B's. All possible strings of this form. So that means the empty string, AB, AABB, AAABBB, and so on. Okay? So that's an example of a language that is not regular, and it necessitates the use of tools that are more general than regular expressions and so on. And those are what we'll cover for this lecture, okay? So this is one example of them, and another example is palindromes, such as W and W reverse. Okay, that's what the R means. Just W in reverse. So like if W is AB, then okay, W is AB, then W R is, you know, BA. Okay. So this is an even palindrome because you don't have something in the middle. It's even length. Anyways, so there are two different tools you can use to describe context-free languages. The first one is context-free grammars, and the second one is called push-down automata. Now, the regular languages that we covered earlier, uh, they have the regular expressions as the counterpart, the kind of tool to recognize them, but they also have something called what's it? like finite automata, okay? Deterministic or non-deterministic finite automata. Push-down automata are kind of the upgrade to the automata that are used for regular expressions, for regular languages, sorry. Except that they have a stack, and this lets them remember things and, you know, do stuff, extra stuff. But it's not, this is not infinitely powerful, okay? Like, there are some limitations. So, with that in mind, let's talk about context-free languages. Now, grammar, sorry. Now, they describe the structure, kind of a string. So let's say, in the English language, a sentence consists of two things. The first thing is a noun phrase followed by a predicate, okay? So it's first the noun phrase and then the predicate, and you cannot deviate from the structure. There has to be first a noun phrase and then a predicate, okay? Now the noun phrase has an article and then a noun, and the predicate has just a verb, okay? Now, examples of articles might be a and the. Nouns might be cat or dog. Verbs are runs and walks, okay? So let's break this down. The noun phrase becomes article noun. So you have article, noun, predicate. Predicate becomes verb, so you have article, noun, verb. And this is the structure of the sentences in this language, okay? So article, noun, verb. And then you replace this with the actual strings. So far, these are things called variables, okay? And they might generate other variables or they might generate actual strings, okay? So an example is you follow the rules. From sentence you get noun phrase and then predicate. From the predicate you get a verb, and then from the noun phrase you get the article and the noun, right? Following that, you can start replacing the variables with the actual strings that they can generate based on these rules, these things called productions. So article, you can choose to have the or a if you want, it doesn't matter. You get different strings, but both of them follow the same structure. They conform to the same grammar, right? So in this example, we chose to replace article with the, so we followed this rule right here. The noun became dog, so we chose this rule, and then walks, we chose the bottom rule a third time, okay? Now, there are 8 possibilities here, as you can imagine, 2 to the 3, but yeah, anyways. You can also have a cat runs, same structure, just different choices, okay? And yeah, here are the 8 strings generated by this grammar. Now, a derivation of, no wait, yeah. I hit the left arrow instead of the down. Okay, production rules. So, in context-free grammars, you have things called variables. You have things called terminals, which are the actual, you know, strings or letters. And you also have the rules in which a variable, you can substitute it with a terminal or another variable or something called a sentential form, which is variables and terminals mixed together. Okay, so here's an example. Let's say your grammar has the variable s, which can produce either terminal a followed by variable s followed by terminal b. Okay, so this is an example of a sentential form because it mixes variables and and terminals, right? So the start of the string, the start of the production will have A, the end will have B, and in the middle S. And then this S can go back and generate another A and B. So you'd have AASBB, or you can have AAASBBB, and so on. Eventually, when you want to stop, you're just gonna replace the S with the empty according to this production, okay? So to derive AB, first you follow this rule, like you have to make a choice if there's multiple choices, like in this case, S can produce either this or that. So you have to choose which one you want to produce. In this case, we choose to produce ASB, and then the S here, for it, we chose to go with this rule to generate the empty string, which means nothing. So we ended up with AB. Okay. Then AABB, same idea. First, we used S generates ASB, and then this S generated ASB again. So we have the A and B from the previous, from the first derivation, application of the production, whatever, the first part, and then you have the ASB from the second part, and then the new S was then used to generate empty. Okay, so you can go as many times as you want. In this case, they go 3 times with ASB, and then they go with the empty, and that gives you AAA, BBB. Similarly, if you go 4 times, you get 4 A's then 4 B's. Now notice this is the exact same language that we mentioned earlier. This one. So empty, AB, AABB, AABB, and so on, right? And that's an example of a string that cannot be generated by a regular expression, or is not regular at all. But we have now the tools to generate it. Just it's not regular. It's context free now. Okay. Anyways, the language of the grammar. So this grammar describes the language that we just mentioned. How crazy is that? Okay. Now, that's kind of just an intuitive overview of the context-free grammars and what they can do, what power they have, that they can generate strings that cannot be generated by regular expressions. So, a grammar, formally, it's a group of 4 things, a tuple. The first thing is the set of variables. The second thing is a set of terminal symbols. The third one is the start variable, and S needs to be in the set V, okay? And finally, a set of production rules, which are the derivations, okay? Okay, well, not derivations, sorry. Which are the, this thing right here. So this is a production, and that's another production. Both of them are using the variable S. And S is also the starting symbol of this grammar. Let me see if there's an example. Yeah. So for this grammar, S produces ASB or S produces empty. The set of variables, well, there's only one variable, which is in capital letters, by the way, if you haven't noticed yet. Okay, and that's S. Okay, so it's just the set containing only S. Next, we have the set of terminals, which are the actual symbols or the letters, lowercase, and that's A and B. Once again, just to be clear, in case you're confused about this, but epsilon is not a letter. It represents the empty string, which means nothing at all. Okay, so it's not counted here. So T is the set A and B. Next is S, which is the starting symbol, and it is in the set V, as you can imagine. Now you can use a different symbol, but all that matters is that it needs to be in this one, okay, in this set. Finally, the set of productions. The first production here is S produces ASB, and the second production is S produces empty. Now, yeah, I mentioned this earlier. Sentential form is a term used to describe a sentence that contains variables and terminals. Yeah, a sequence of variables and terminals. So all of these are sentential forms because even though they do have terminals, they also have variables. So these cannot be considered the final string, okay? This sentence is the final string. So these are not outputs of the grammar. ASB is not an output of the grammar, nor is AASBB. Once you get rid of all the variables, by applying rules repeatedly, you're going to arrive at something that is actually generated by the grammar, and that's AAA and that's part of the actual language. But AAASBBB is not part of the language. It's only a sentential form that is kind of an intermediate thing on your way to generating something that is in the language corresponding to this context-free grammar. Okay? Next. A bit more notation. So this double arrow is used to represent you kind of applying a production. So S has like there's a derivation S. ASB is derived from S, then AASBB is derived from ASB, but this corresponds to only a single application of a single rule. But what if you want to kind of have a shorthand for saying that this symbol or this variable eventually derives this string, okay? In this case, you just put a star over the arrow, and this just skips all the steps. You don't need to write them, but like they're implied by this, okay? Like there exists some sequence of derivations that takes S and produces AAABBB, okay? So, yeah, in general, sentential form 1 eventually derives sentential form Wn, okay? If W1 derives W2, which derives W3, and so on up to Wn, okay? Obviously, if you don't apply any productions, then the recursive case is correct. Anyways, this is true. This is also true because eventually, if you first, so for this one, if you apply this rule, then yes, it's true, right? If you apply the first rule, then the second rule, then you arrive at AB. For AABB, you apply the first rule twice and then the second rule once. And for this one, well, you apply the first rule 3 times and then the second rule. So all of these are kind of like shorthands instead of having to write the entire derivation. Okay. Moving on. Yeah, on the left side here, you can have a sentential form as well, obviously. Let's keep going. We have a second grammar, finally. S produces AB. A produces AAB, and A also produces empty. So you can choose between them, either A or empty. Now, what is this? Notice that S only appears once, and it's not produced by anything here, okay? So you start with S, and then you're never gonna get AB again, like just AB. You're not gonna produce it by itself again, because S isn't produced anywhere. So anyways, this is kind of stages property of some context-free grammars where, okay, you're kind of like past the point where you cannot make certain derivations or productions anymore. And that prevents you from doing certain things. Anyways, so S produces AB. And then A might produce empty, or it might produce A, capital A, B. Okay? So some of the derivations are S produces AB and then B. S produces AB, then AAB, and then the B from the S right here. And A produces empty, so you get ABB, right? And you can repeat this multiple times. Now, the thing that you cannot repeat, because you cannot access S anymore, is having this B at the end. So, if you look at the strings generated by this, there's always one more B than the number of A's. So, you have 0 A's here, but 1 B. You have 1 B here, but 1 A here, but 2 B's. You have 2 B's here, 2 A's here, and 3 B's. So, whenever you want to kind of add a restriction in this way, that okay, first I'm gonna generate the b at the end, and then and then before that we're gonna have the usual grammar that generates a n b n. Then this is kind of the thing you have to do. So you have to do it in stages. Okay. Anyways, yeah, this is the uh, general form of the strings that are generated by this language, a n b n b, or you can say a n b n plus 1. Moving on, yeah, the if you put L parentheses G, then that's the set of all possible strings generated by the grammar, starting with the starting variable, right? uh, okay. Notation here. If you have two or more productions that have the same variable on the left, then you can just put both of the results and separate them with this kind of pipe, okay? So if A can produce AAB or it can produce empty, right? So this is what the pipe means. A produces AAB or empty. Similarly, with the article that we saw earlier, article produces A or the. Okay? Moving on. Yes. This grammar that we saw earlier, it does actually have a kind of real life application, if you will, where the if instead of A you had the left parenthesis and instead of B you had the right parenthesis, then look at that. You have some number of left parentheses followed by the same number of right parentheses. So imagine that. Next, you have this new grammar. S produces ASA, S produces BSB, and S produces empty. So from the outside in, you have A, B, and from the right side left, you have A, B. Okay, so this is kind of palindromes, even palindromes, that is. Okay, so let's say we generate, let's see if there is any other examples. No. Okay. Ah, yes, there is one. I skipped it somehow. So you go with this rule, rule 1, ASA, and then the S produces BSB because of this rule. And then the S here produces again ASA thanks to this rule. Like you can go over and over again, okay? Once you have an S, you can choose any one of these that you like. It doesn't matter, okay? And that's why sometimes when you have to have like a restriction where you're not allowed to use the rule again, then you have to use a different symbol, okay? So just keep that in mind when you're generating, when you're creating new grammars for certain types of languages. So this S, this time we chose to go with empty, so we have ABA, ABA. Now, right side and left side are mirrored. Now, in this case, it's not really a good example because you can also go either way. So, yeah, whatever. Anyways, point is, this is the grammar that generates this language. Now, moving on to this one. This one's kind of interesting. So, S produces ASB. We saw this with the ANBN language, or the left and right parentheses language. These ones, the nested parentheses. And if you add this rule, S produces SS, then what you get is, yeah, this is more interesting. So if you go with SS and you produce ASB on the left with this one, and this becomes empty, see here. And then this one also produces ASB. and then this one produces empty, you get AB and AB, which is the same as left right parentheses, left parentheses, and right parentheses. Okay. Now, this is kind of a more general grammar than the one that we saw, this one, in that it lets you have multiple pairs of parentheses. They don't have to be perfectly nested, like just one inside the other. You can have them side by side or whatever. But point is that every parenthesis is always matched by a right parenthesis, and kind of you don't like break that at any point. There's no one that's matched by a different one that was generated by a different S. Okay. So this is kind of wordy, but the point is the parentheses are always matched together, okay? So this one and this one were produced by the same S, as were this one and this one. So this was from like an A, S, B production, okay? Where the S generated these four, okay? And then you have these that were also generated from S, and you see this is SS from this rule. So you can kind of see the parallel between that. We already saw all of this and that. Yeah. Now, what is a leftmost and rightmost derivation? Leftmost is when you have a sentential form with multiple variables in it. So let's say AB, that's two variables. You always derive with the one on the left side more first, okay? So in this case, it's A, and the A produced AAA by this rule. Then the leftmost variable is again this A, and in this case they went with empty, so you're left with AAB. This B produces BB, and then the only variable is here, and it's a leftmost one clearly, so you use it to produce this. Okay. Now, similarly, the rightmost derivation is when you go from the right side. Okay. So S only one variable, you go from the right side. It's the rightmost, right? So it produces AB, and you go with the rightmost one here. So you choose BB, and then this B produces empty, as you can see. And then the rightmost variable is the only one here, A, so that produces AAA, and then it produces empty. Now we have another one here. Okay. So here's another derivation with a different grammar. So S produces A, capital B. Leftmost derivation, we choose the A and generate BBB. This B is the leftmost variable, so we use it to generate, in this case, A. And then since this A is the leftmost variable between A and B here, we choose this one, and we choose BBB again, so that's that. And then this B is the leftmost variable. In this case, we choose the empty, so that's it. And this is the only variable left in this sentential form, so we chose the empty in this case, and that gave us the string. Rightmost derivation, same idea, except you go from the right side. So this B produced empty, and then it's the same B that produced the empty here, just to be clear. And then you're left with AA. This is the rightmost, obviously, so it generates BBB. The B here generates A, the A generates BBB, and then the B generates empty. Now, what's a parse tree? It's kind of a drawing, a tree, you know, that shows the actual derivation. So S produces AB, you have the starting symbol as your root of the tree. Then on the left side, you have this guy, and on the right side, you have this guy, okay? leftmost derivation, this guy produces AAA, so we have that here. And, well, okay, it's not leftmost derivation, never mind. We're going like breadth first in a way. So B here produces BB, so that's what they did here. And then this A produces empty, and there's still one more variable, which is this one, and that one's gonna produce empty. So the result here, you look at the leaves. A, empty, empty, you just ignore those, and then B, right? So the string is AAB. Here. Now, some grammars have ambiguity, where the same sentence or the same string can be generated in two different ways, okay? So let's go through this example. You have the grammar E produces A plus E plus E, or E times E, or E in parentheses, or A. So this is supposed to describe like some kind of arithmetic, right? And an example of the strings that can be generated by this is A plus A times A, right? So here's an example of a derivation here. So first you go with E plus E, and then the leftmost E generates A, while the rightmost one goes with E times E. And then the two E's generate both A's. So yes, you have A plus A times A, right? Now let's do the rightmost. No, wait, never mind. Leftmost again. But you choose different rules this time. My bad, I didn't actually read ahead these slides, so I'm just going one by one. Right, so E produces E times E this time. And then leftmost, so you go with this one now. So this produces E plus E. The E's produce A, and then A. And then this E produces A. So you have A plus A times A. But would you look at that? Exact same string, but the first time we went with plus, and the second time we went with times. So what's going on here? Well, this grammar is ambiguous because there are two different derivation trees or parse trees for the same string. And that's kind of an issue because we want to have a clear, obvious structure. So for the same string, we need to have kind of exactly how we should read it, okay? Like which part is part of which part, okay? So on the left side here, we have that the multiplication is part of the addition, okay? But on the right side, we have that the addition is kind of like a substructure of the multiplication, and that's no good, since it can go either way according to the grammar. So that's kind of an issue, isn't it? I think in this course we don't really focus on it too much, but in compiler design, which runs during the springs, we'll see some techniques for how to remove ambiguity and so on. Okay, so yeah, this is just an explanation for why we should care about ambiguity. It can give you different results according to how you interpret the string, so you have to have an unambiguous way to interpret the string, okay? So that's the point of it. So let's say a is equal to 2. This is 2 plus 2 times 2. So first you do this part, the smaller part, the sub part, which gives you 2 times 2 is 4. So 4 plus 2 gives you 6. Now the other way around is 2 plus 2. This gives you 4. And this is also 2. Horrible. Okay, so 4 times 2, that gives you 8. So which one's correct? Obviously, according to our understanding of arithmetic, it should be this one. And yeah, that's why ambiguity is bad. Here's another example of an ambiguous grammar. If statement. So you have two choices here. If expression, then statement. Or you have if expression, then statement, else statement, right? Now, the ambiguity here arises with the statement because the statement can give you another if statement, okay? This isn't really clarified in the example, but just pretend that statement is another if statement, I guess. I don't know. It's like statement can generate another if statement. Anyways, so if statement generates if expression 1, then statement. And then the statement here is an if statement and generates if expression 2, then statement 1, else statement 2. So the first time they went with this one, and then they went with this one, okay? Now, the second time, they went with the second rule, and then with the first rule for the statement over here, okay? And that's the issue, because if you look at the leaves, if expression 1, then if expression 2, then statement 1, else statement 2, okay? And if you read that for the second tree, if expression 1, then if expression 2, then statement 1, else statement 2. So it's the exact same string as we can see here. And yet we have two different derivations. One of them chose to go with the first rule at the start, and one of them chose to go with the second rule for the first derivation. Okay. Also, yeah, this is just some general information about ambiguity. We're not gonna actually solve ambiguity in this course. But anyways, yeah, some context-free languages have only ambiguous grammars. There's no way to kind of have uh, an unambiguous way to describe the structure. So you're left with what you have here, okay? So L is the union of AN, BN, CM, where N and M are integers. Yeah, union with AN, BM, CM, okay? So unions, usually you can use the pipe to describe them. So L has the starting symbol S, which produces either S1 or S2. S1 is for this part and S2 is for this part, okay? Now S1 has S1C or A, and A has AAB empty. So this is the phases thing that I was talking about earlier. So first you're gonna generate multiple C's possibly, or just none of them at all, or one or two. Anyways, once you're done generating C's, you're gonna move on to the A's by generating a single A, and then you're gonna have no more S1s, right? And then the A's are kind of the next step of generating a string in this grammar, where the A's generate AAB, okay? And you can have this multiple times. Similarly, AN, BM, CM. So S2 is the first phase, where you first generate some number of of A's, as many as you want. And once you're done, you're going to generate a B, and then the B generates BBC repeatedly, okay? So B, B, C, B, 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 C. Well, the third B is capital, and so on until you're done, and then you're going to have empty, right? Now, what if N and M are the same? Then you can go either way, okay? So no matter what, you can't get rid of this ambiguity. In which case, the techniques from compiler design won't be very helpful, right? But don't worry, because this kind of language is not really useful for programming languages anyway. So yeah, there might be some exotic counterexample, I don't know. But yeah, so let's do some exercises. Slide 80, we're more than halfway through. Okay, first one. W contains at least three ones. Now you remember how to do this with the regular expressions, right? We saw the example earlier with the at least two zeros or the at least one zero. You just need to do that multiple times. So the way to do this is you first generate all the ones, okay? So actually, let me just clear this and go to the answer. So first you generate all the ones, x. You have multiple x's, and between them are three ones, right? And then the x's can generate whatever string, okay? Just the important thing is that there are three ones. This is the exact same thing as this part is the exact same thing as the 0 plus 1 star that we went over before, okay? Just in between them, no matter what, you have the three ones. Now, if you if you write down the formal definition of this grammar, the V, the set of variables, is S and X, okay? Sigma, which is the set of symbols, or the alphabet, or the set of terminals, if you will. That's 0 and 1. S is the starting symbol, which is in V, and P is the set of productions, these, and, well, this and these, right? So that's four rules. Next, W equals the reverse of W, and the length of W is even. Okay. So this is palindromes that are of even length. And we went over this example already. ASA or BSB or empty, right? Same idea. Next one is the length of W is odd and the middle symbol is 0. So in total, since it's odd, that means the length is in the form 2n plus 1. And the middle symbol, which can be considered as the 1 here, is 0. So you have the 0 and then n symbols, some number of symbols, and that's n, and then the same number of symbols on the right, okay? Now, the symbols here can be anything, can be zeros or ones. They don't have to be the same even, okay? So what you're going to do here is you're going to have S produces 0s0 or 0s1, because the two sides don't need to matter, don't need to be the same, right? Or 1s0 or 1s1 or 0. So what happens here is that when you're still generating the parts that are on the outside, you're going to choose one of these four rules. So it can be 0s0, 0s1, and so on. Okay, a couple of examples of strings might be: first you generate 0s0, and then the s generates 0s1, and then the second s produces 0. So you have 0s0 gives 0s1 0 because of this second rule here, okay? And then this gives you 0 0 0 1 0, okay? So that's odd length, and the middle symbol is 0. Now the other way to do this would be to have S produces X, S, X, or 0, and then the X is 0 or 1, okay? This is, I believe, the example that was the solution that was given by the professor when we solved this in the lecture. Both of them are completely valid and equivalent grammars, so don't worry about it. Now this one's a little more interesting. So A to the I, B to the J, and C to the K, where either I equals J or I equals K, or both. Okay? So it can be that these two are equal, or these two are equal, I and K. So you have two choices here, okay? This might look complicated at the start, but let's take it step by step. So the first thing is your starting symbol, and starting symbol can give either, let's say, a I, B, I. Now notice this is the case where I equals J, and then CK, right? Now this is one example, one side of the language. The other side is if I equals K, in which case you have a I, B to the K, or J, whatever, and then C to the I, right? So we're gonna have a possibility for each one of these. Let's say this is S1 and this is S2. So this is S1 or S2, okay? Next, for S1, you're gonna have that you're generating CK, multiple C's, and then you're gonna generate the A's and the B's together, okay? Because you have to generate them together in order to, you know, have the number be equivalent, okay? So you can actually do this in kind of like two phases as well. So the first part is to generate the A's. Let's say this is A, and the second part is to generate the C's, right? So we're splitting it into kind of two different parts. The first part will generate AB, or ABB, or AABB, and so on. And the C here will generate multiple C's. So A produces A, A, B, or empty. So this is recursive. It can generate AB, ABB, AABB, and so on, as I literally just said like 15 seconds ago. Okay. For the C, that's going to generate C, C, no reference intended to a president of a certain country. So CC or empty. So you can immediately go with the empty, in which case you generate no C's at all. So K is equal to 0, which is allowed, by the way. Or you can generate 1 recursively, or 2, or 3, or 100, as you like. Okay? So that is for the I equals J part. Now, for the I equals K part, you're going to do things a little differently. So let's go down here for some extra space. S2. Now, the phases aren't as clear as, okay, first this and then that. No. I mean, sorry. The phases aren't as clear as splitting it into two parts and doing them separately. What you're going to do is you're going to have first, you're going to generate the outside. So the A's and the C's together. And then once you're done with that, you're going to go with the B's. Okay? So this can be recursive. You can directly say A S2 and then C. And you can repeat this multiple times. So A S2 C, A S2 C C, and so on. Okay? Eventually, you're gonna stop and you're gonna move on to the next phase, which is generating the B's. And the number of B's is completely separate from the number of A's and C's. Okay? So let's continue. For the B's here, you're gonna have B terminal and B variable or empty. So once again, this is recursive. You can generate as many B's as you want, completely independent of the number of A's and C's. And eventually you're gonna have empty, and that's gonna be the end of your derivation. Okay? Now, let's see what we have here. The answer did not bother going with S1 and S2, kind of. W here corresponds to S2, but they skipped S1 and just put directly XY, which is the same as AC, okay? But other than that, conceptual, kind of easier to understand difference, it's the same grammar. Next, okay. I, A to the I, B to the J, C to the K, where I plus J equals K. So the number of A's plus the number of B's equals the number of C's, okay? Now this one also needs kind of a different kind of thinking in a way, similar to the previous example. So let's look at an example. First, suppose you have A, B, B, C, 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 okay? So you have 5 letters on here and 5 letters on here. The number of A's plus the number of B's is equal to the number of C's, right? Now, what you're gonna do here is think from the outside in, okay? This is the thing with context-free grammars. Usually you're kind of going from outside in. But you just have to determine where to make the cuts, kind of. If that makes sense. So in this case, you can make a cut here and here, okay? So you have the A's and 3 A's and 3 C's, and then you can have 2 B's and 2 C's. Okay? So this gives us insight into how to formulate the grammar. So what you're gonna do outside in, first you're gonna generate the A's and the C's together, 1 A for every C, or 1 C for every A, same thing. And then once you're done with that, you're gonna start generating B's and C's together. Okay? So let's start. First we have S produces A S C or well T. Okay? So you're gonna generate the A's and C's together recursively, and whenever you're done, you're gonna switch to the next phase, which is T. And then T is gonna generate the B's and C's together, right? So you're gonna have B, T, C, not a cryptocurrency. Okay? And whenever you're done, epsilon. So yeah. That's the context-free grammar for this language. Now, I'm not gonna bother with this one because it's kind of boring. Let's just go over it quickly. The question asks to find two different, well, the leftmost and the rightmost derivation for this string and also the parse tree. So let's go through it. S produces BB and that produces, well, BBB, BBAB, BBAAS, and so on. So you're going with the leftmost variable each time. So that's why this one produced an A and so on. Okay, similarly with the rightmost derivation, you get some stuff. And you get the sparse tree. Now, if you were with me in this lecture, this grammar is actually ambiguous, despite what the well, I think there was text that says this grammar is unambiguous, but no. I'll leave it to you to work it out how this is actually ambiguous, but it doesn't really matter. Let's move on. Abstract syntax tree, that's kind of like a shorthand for the parse tree. So the parse tree shows you all the derivations, literally everything, but the syntax tree just shows it in brief, okay? Now you've taken data structures and algorithms, right? It's a prerequisite to this course. And if you remember, there's something called the infix. No, wait, no, not infix. Okay. Uh, in order traversal. Okay. So what happens here is that when you're traversing a tree, you're going. Let's say you have like a node with two children. In order means you first go with the leftmost child, well, the left child, followed by the root node with the parent, and then the right child, okay? And if this one also had its own children, then what you're going to do is first this guy, then this guy, then this guy, and then this guy, okay? So the algorithm is, let me redraw it again. Okay. So this is the root. You're gonna, okay, you have this in mind, but you're gonna start by looking at the left child, okay? So you go here. And then this guy has its own children, so you're gonna start with the left children, left child first. So you go with that, and then you go back to this one, and then you go back here, and then you realize, oh, okay, there's no more children here, let's go back a level. So you go up here, you print this guy, or whatever you do with it, you process it, and then you go down to the right children, okay? So this is the idea of the abstract syntax tree. It's the same idea, 1 times 2 plus 3. That's the string generated here. Abstract syntax trees may also do away with terminals that are redundant once the structure of the tree is determined. So the parse tree shows everything. So you have the if, you have the parenthesis, you have the expression rule, you have the right parenthesis, the statement, else, and the other statement, right? So the parse tree is going to show all of that. But the abstract syntax tree might avoid that and just keep it down to only the the non-terminals, the variables. Okay. More of that, I don't think it really matters. Same kind of idea. Okay. Now, the emphasis here is that this is a huge, relatively compared to what we saw, parse tree, right? But if you look at the corresponding abstract syntax tree, it's actually pretty small and manageable. So that's kind of the point. It's a compact form of the parse tree. Moving on to the BNF. BNF is Bacchus Nor form, and it's basically just context-free grammars, except written in ASCII. Okay, so this is kind of a way to be able to write them in in yeah, on a computer, right? Like without making use of any special hardware or software, sorry, or whatever. So, general information, you don't need to worry about that. Okay. So, the angled brackets mean a non-terminal, as stated here, and that's a variable, okay? Non-terminal variable, same thing. The colon equals is the same thing as the right arrow in the context-free grammar. This is another variable This is the same pipe symbol, that means then or. This is another uh, two variables. So if we were writing this as a context-free grammar, it would look something like n produces d or n d, right? And then for the digit here, we're gonna have, like, for example, d produces 0 or 1 or 2 or 3 up to 9. Okay. Here are some more examples. First one is the while loop, which is, you can say, for example, w produces the symbols w, h, h, I, l, e, the symbol left parenthesis, and then this variable condition, which you can see like it's capital C or whatever, and so on. Okay. Another BNF. You can write this in the usual context-free grammar notation if you like with the arrows and so on. It doesn't really matter, okay? They're completely equivalent. Each thing in here corresponds to something in the grammar. It's just a different notation that's easier to write on computers. Now, what's interesting or more challenging, let's say, is the EBNF, Extended Backus Norm form. And what this one's about is it adds a few notations that make things a little more concise. So context-free grammars, you saw how at some point we had like a really long grammar with like, yeah, 6 variables, 1, 2, 3, 4, 5, and 6, right? You could make it a lot simpler if you use EBNF. So this makes things more concise, actually even easier to understand, even if they're more kind of almost too concise in a way, okay? Because you don't need to have so many different rules in your head at once. So the extensions are the star, the Kleene star, the Kleene cross, which means one or more. I think I just glossed over this when we went over it before, but you know, a star is the same thing as a plus, okay? Just to be clear. So at least one A. That's the point here. And then you have the question mark, which means 0 or 1 occurrences. So let's say you have, okay, well, an EBNF, it would be a pipe, so A pipe B. So this is A or B. You group them. This is still A or B, right? So from this expression, you're gonna get either an A or a B. Now, if you put a question mark here, this question mark applies to the entire group, and it means A or B or nothing at all, okay? That's the point. Moving on. Yeah, so this is a comparison, an example of a grammar in BNF, and the same grammar, completely same like language generated by it and so on, but in EBNF, okay? So this one has 4 variables with, as you can see, 1, 2, 3, 4, 5, 6, 16 rules or productions, right? Okay, let's not count the digits. That's 6 productions here. For this one, do you see any pipes here at all? No. And that's what makes this so concise. It's only a single rule, just kind of slightly more difficult to read. And this says that the minus sign is optional. You can have multiple digits, but without having to work around, you know, the recursive stuff in the in this rule over here. Okay, so you don't need to have all that. Instead, you can just put directly digit plus, which means multiple digits, at least one of them. And then this entire part is optional, which is the part with the decimal point and the digits after it. So if you want this, you're gonna put the dot and then multiple digits, right? And the digits, well, you can't really work around having 0 and 1 and 2 and 3 and 4, right? Anyways, uh, you should go through these by yourself to understand like how to convert a BNF grammar into eBNF. I'm not gonna bother explaining that. Just kind of get an idea of like what recursive stuff you can make a shorthand out of into like a plus. I think there was like a brief set of rules for how to do the conversion. I guess not. Okay. Or yeah, no. Okay. So this is a summary of BNF and eBNF. For syntax diagrams, now these are based on eBNF, okay? What you have is terminals, which are in ovals or in circles. And then you have the variables or non-terminals, which are in rectangles, okay? When you have arrows, that's just like a one by one kind of thing. If you have two arrows going out from the same place, like here, for example, you can have either this arrow or this arrow, right? So this is a choice. Now, you can choose from wherever you were coming from, like let's say here, you can choose directly to go here, or you can choose to go here as many times as you like and then leave the loop, right? So this represents the Kleene star because let's say 0 terms or 1 term or 2 terms and so on, or as many as you want, okay? Next, you have the OR in the pipe, in which you can go here and then you either go to this one or to that one, okay? For the question mark that we saw, the optionals part, so you can have either this or something, right? So this bit is empty completely. Then this part will has a single occurrence of this stuff. There's no looping, just else than statement. Okay. Recursions allowed where it cannot be replaced by repetition. Okay. So let's go back to this grammar for expressions. So an expression is a term, well, it's a sum or difference of terms. So you have a term plus a term minus a term, as many as you want. Okay. But you can also have just a single term, and that's why this is in a star. Okay. When you have a star, you can have an arrow just going directly to the end with a branch that loops through some other stuff, okay? Which is the stuff in the group, okay? Now the first part in the group is either plus or minus. So you have some branching here, either plus or minus. And following the choice, you have a term. So wherever you go, you're going to go back into this term and continue on, okay? Options easily shown as an alternative that passes through no elements as in the if rule from the section of ABNF. So yeah, like we saw, just passes through with no elements, or you can go and choose this if you want, okay? So a couple of examples. I'm not gonna bother because this is the same stuff as the exercises with generating grammars, except you write it in BNF. Now, what's interesting is when you go with the eBNF, okay? So this is a recursive rule, AS or empty. And yeah, by the way, with the empty, you do have to write the angle brackets. I forgot to clarify that earlier. With the BNF, you can just directly put the star and get over it, okay? Uh, Similarly, this is just a plus and you don't need to do the recursion anymore. But you do still have to have the 0 and 1 and 2 and 3. Now, if you're being 100% correct, you're gonna put quotes around each one. I think in the homework I did that, but you don't need to bother. It literally, like, it doesn't matter too much, okay? Don't worry about it too much for this course. Construct a BNF grammar for a set of all strings consisting of one or more A's with a comma between each A and the next, okay? So, A, comma, A, comma, A, and so on, okay? Now, there are two ways to read this. The first one is if you group the A and the comma in this way. So A, comma A, comma A, comma A. And this one's by itself, okay? Or you can have A, comma, A, comma, A, comma, A. So you're instead grouping them in this way. These are two different ways of approaching the same well, problem. Both of them are completely valid. So in this case, they went with the first one, or sorry, yeah, the second one, sorry, where you group A, comma, A, comma, and then the last A is by itself with no associated comma, like it's not being linked to the comma that's before it, okay? And the S here is, the EBNF is just a more concise form that uses the star instead of recursion, as usual. This one's a little more complicated. It uses the same idea of the comma, where the digit list is either a single digit or a digit followed by a comma and then another digit list. So eventually you're gonna end with just a digit right here, okay? In that way. Next, constructing syntax diagrams. I'm just gonna skip this one, and yeah, that's the end of the lecture. So, how much have we been going? 70 minutes for this one recording, this one shot. So that's not very good, is it? I'm not sure if we'll be able to release this in time. Anyways, it might still be helpful for the following year, I hope. Okay, that concludes the lecture. See you. Okay, moving on to lecture 7 on semantics. This is going to cover the meaning of the programs rather than the structure, as we saw in the previous lecture. So, yeah, let's get to know it. Specifying the semantics of a programming language is more difficult than specifying the syntax because, yeah, semantics is about meaning, which can be kind of difficult to explain sometimes. Semantics, we have the context-free grammars and the BNF or EBNF, which help us formally specify exactly what we mean and what's valid and what's not valid in the programming language. But with semantics, it's kind of hard to determine sometimes. Okay? Now, let's get into it. Let's talk about attributes. The meaning of a name, like the name of a variable or whatever, in a program is determined by the properties or the attributes that are associated with the name, okay? So this is the name of something in the program written in C, and this declaration associates the name n with the type constant integer and the value 5, okay? So what this slide says is what I just said. The declaration itself associates to the name n the data type attribute integer constant and the value attribute 5. Okay? Now, this declaration int x does the same thing. It associates the type integer to the name x. No value because there's no value given in the declaration. Now, This declaration is for a function. It associates the name f with the return type double and these parameters, in this case only one parameter, which is of type int and of name n, and it also associates this bit of code with f. Okay, so let's read this now. Same thing what I just said. The declaration associates the attribute function and the following additional attributes to the name f. First additional attribute is the number, names, and data types of the parameters. So in this case, int n, a single parameter. Second thing we have is the data type of the returned value, which is double. And the third thing is the body of code to be executed when f is called. Okay. Now, declarations. So far we've only seen declarations: const int n equals 5, int x, double f, and so on. Okay. Now, you can also have assignments that would change the meaning of some thing. Okay. So int x had no value, or well, 0 initialized, I guess. But this assignment messed with the meaning and assigned it a new meaning where the value is equal to 2. So now, after this point in the program, whenever we see x, that means 2. Okay. Now, these constructs that associate a name with some value or with some attributes are called bindings. Okay. The process of associating an attribute with a name is called binding. Okay. And binding has two types. One of them is static and the other one is called dynamic. And this refers to the time that the binding happens at. Okay. Now, static binding is when the binding occurs prior to the execution of the program, which means it's done by a compiler, for example. Okay. But for dynamic binding, this occurs during execution. So with an interpreter, for example, Python, you're just saying x equals 5. You're not saying this is an integer. And then later on, you can say that x is actually equal to the string hello world. That's totally fine. Dynamic binding, you can change it whenever you like during the execution. In addition, there can, of course, be some amount of dynamic binding in a statically compiled program. For instance, if you're changing the value of of a variable during execution, okay? Changing the value counts as a type of binding, and so the assignment x equals 2 binds the value of 2 dynamically to x, okay? So that's a type of dynamic binding, even with a statically compiled program. The C++ statement y equals new int, which you've seen in data structures and algorithms, it dynamically binds a storage location to star y and assigns that location as the value of y. So what's going to happen here when this is executed is that the C++ runtime finds like an empty place in memory and takes the address of that place and associates it with the name y. Okay. And so when you refer to star y, it means the actual value there, and when you mean y, it's the address of that value. Okay. But this is done at runtime because, well, who knows what kind of circumstances and things might change with every time the program's executed. It might proceed a little differently each time. Moving on. Bindings. Now, here's the thing. We're discussing this all in the abstract, but when you come to actually implementing it, you need to have some kind of data structure which stores all the information about every single name that is in the program. Okay. Right. So the symbol table in the abstract is really just a function that maps names to attributes. So for example, the name n is mapped to the type attribute constant integer and the value attribute 5. Okay. and the symbol table just keeps track of this information. Now, symbol table changes as the program gets translated or as the uh, program gets executed. And the reason is because it needs to keep track of changes in the values and possibly the data types in the program. So at the start of the program, the symbol table will look completely differently from the end of the program. Okay. Now, the translation of a program has three phases. First one is lexical analysis, which traditionally has to do with regular languages and regular expressions, and it determines whether a string of characters represents a token or a single kind of unit in the vocabulary of the language. For example, there are three tokens, or rather lexemes here. First one's int, next one's x, and this one's a semicolon, right? Now, this int here is a keyword, the x is an identifier, and the semicolon here is, well, the semicolon, right? Now, this is lexically correct because each individual atom, let's say, of the statement is correct in its formulation. Now, in this case, this thing is not valid. It's not an integer, sorry, it's not a data type, it's not an identifier, it's not anything, okay? It's not lexically valid in the language. So this thing is the kind of thing that is the kind of error that is caught in the lexical analysis phase of translation. Next, you have syntax analysis, which uses the context-free grammars that we saw in the previous lecture. And rather than checking one by one each of the lexemes, it looks at them together to understand the structure of the program, okay? So this set of declarations has a certain structure. First, you have the data types, then the data type, sorry, then the identifiers, comma separated, then the semicolon to end the statement, okay? Also, this assignment statement is valid because it has the correct syntax. You have an identifier, then the equals, and then some expression, and then the semicolon, right? Finally, you have this thing which is not syntactically valid because there's supposed to be some operator here. Usually, well, we would want the equal sign, right? So because that's missing and you have an identifier followed by another identifier, that doesn't really make sense in the grammar of the language, and so it's considered syntactically incorrect. Finally, we have the static semantic analysis, and the static occurs during the actual translation or compilation of the program, as opposed to dynamic semantic analysis, which is during the actual runtime, okay? So this is concerned with establishing the attributes of names and declarations and ensuring that the use of these names and references conforms to their declared attributes. What this means is the way that you use these names, these variables or constants, should match what their types are, okay, or their attributes. For instance, you have two integers, x and y. X equals x plus y. This is totally fine. You're adding an integer with another integer, for example, okay? Now, this is semantically incorrect because in this case, we didn't declare what z is, okay? Because of that, there's no way for us to tell how we should interpret the meaning of the statement, okay? So that's an example of static semantic analysis. Now, let's read the slide. During the execution of a compiled program, attributes such as locations and values must also be maintained, okay, during the execution. A compiler generates code that maintains these attributes and data structures during the execution. The memory allocation part of the process, that is, the bindings of names to storage locations, is usually considered separately and is called the environment, okay? So the mapping of names to locations in memory, that's called the environment. The bindings of storage locations to values, okay? So you have names to locations and then locations to values, okay? And this is called memory, since it abstracts the memory of an actual computer. It's also called the store or the state, okay? Anyways, bindings can be determined by a declaration either implicitly or explicitly, okay? So this is explicitly saying that the type of X is integer. So this declaration establishes the data type of X explicitly using the keyword int, but the exact location of X is only bound implicitly. So we don't know where exactly in memory X will be. That's up to the compiler, not us as the programmer. Okay? And similarly, the value of X is either implicitly 0 or undefined, depending on the location of the declaration. So sometimes we can determine this based on like the rules of the semantics of the language. Other times not so much. Anyways, but this explicitly binds 0 to be the initial value of X. So now, rather than having an implicit uh, initialization of X, you're going to have it explicitly set to be 0. Now, not only can bindings be implicit in a declaration, but the entire declaration itself may be implicit. For example, in Python, you don't need to declare integers or variables in general, okay? You can just say x equals 5. You're not specifying the type of x when you first introduce it. You just say x is 5, okay? So this automatically does the binding right then and there. And you can actually also follow it up with a different type, I believe. I'm not really a Python programmer, so I'm not completely sure how this works, but at least from what I'm looking at here, you can change even the type dynamically. So yeah, that's kind of cool. Moving on, declarations and blocks. So we know what declarations are. We covered those already. And blocks are basically kind of logical parts of the program, and they include both the declarations first and then the actual assignments and computations, okay? And they're separated or like denoted by some kind of syntactic marker from what's being said here, such as braces, so opening brace and ending brace, or like keywords, begin, end, or whatever you like, okay? And this is just an kind of an abstract thing, although some languages actually require that you go with this structure. Anyways, in C, blocks are compound statements and appear as the body of functions in function definitions, and also anywhere an ordinary program statement could appear, okay? So the body of the function P is, as you can see, a block. And then the main block has first declarations, followed by a bunch of computations. And in between those, there's another block, which starts with declarations and then some computation. Okay? So yeah, blocks can be nested as well. Okay? Moving on, declarations that are associated with a specific block are also called local, while declarations in surrounding blocks or global declarations are called non-local to the function or the location memory in the program, okay? So int x and double y here, they are global because they're outside of all of the functions and you can access them from anywhere you like. And then main here, the declarations of I and j are local to main, okay? And if you had another block, some stuff here, then I and j would be non-local to this block, okay? The notion of blocks containing declarations began with algol 60, and all algols descendants exhibit this block structure in various ways. For example, in Ada, a block is formed by a begin-end pair preceded by the keyword declare. So declare, you put the declarations, and then begin and end has the actual computation that you want to do with those uh, variables here, okay? Now, in block-structured languages, blocks can be nested to an arbitrary depth, and names can be redeclared within nested blocks. Instead of identifying each new declared name with a unique integer counting from 0, we can associate with each declared name a level number and an offset. This pair of numbers is called the name's lexical address. Let's see if there's an example. Okay, I honestly don't remember this from the lecture, but anyways. So in Ada, you have two nested blocks here. Here's the inner block and here's the outer block, right? Now, the outer block has lexical address 0, okay? So the variables that are local to this block have the first part of the lexical address as 0, and then the inner block, the variables in it, even if they have the same name, they have a different lexical address because the first part of the lexical address is 1 instead, okay? So that's kind of the idea here, more or less. Then the second number just determines which of these kind of names are within the same block. So the 0th one is the first one, or X. Then the 1 here is the second one, which is Y. I guess that's what it is, more or less. Anyways, scope of a binding. Declarations bind various attributes to names depending on the kind of declaration. The scope of a binding is the region of the program over which the binding is maintained, and sometimes by abuse of language, we refer to the scope of a name. However, the same name may be involved in several different declarations. So the point here is that some names don't make sense outside of a certain scope, okay? And you've seen this already in C++, right? The character Y doesn't have any meaning outside of the range, like the lines 3, 4, 5, okay? Like if you try to use Y here, you're not gonna get any result. Similarly, if you try to use Z at this point or at this point, it's not gonna make sense. Z only makes sense within the function Q. So that's kind of the scope. Obviously, global declarations such as with X they make sense everywhere. Okay, so let's see where this is. Y is only defined here. So when you see Y, you're gonna add it to the symbol table with type character and so on. And once you see the closing brace here, then you're gonna remove the entry for Y from that symbol table, okay? Now, P as a function is has a global scope in a sense, because after you declare it, you can use it anywhere after that, but not before that, and that's why the scope begins from the line on which it's declared. Okay. Similarly with Q, it's usable everywhere after the declaration, but the variable Z that is local to Q is only usable from within Q. Okay. Same thing with main, with W in main, and so on. And for X, since it's a global declaration here, it's usable anywhere. Okay. Next, in Ada, you can actually name blocks, like give them different names. So for example, you can name the outer block here by B1 and later use like B1.a. Okay. So, okay, let's go over this example from scratch. So you have the outer block B1, and it has all of this stuff. And then the second block is B2, and it contains all of this code. Okay. So in B1, you have two variables A and Y, and in B2 you have A again and B. Okay. Now, when you want to use Y inside of B2, you can just say Y. But when you want to use A, then which A do you mean? If you want to refer to the A defined in B2, well, it's the local one, right? Since it's a local A, you can just refer to it by A. But if you want to refer to the A from the outer block, then you can say B1 dot A, and that's gonna refer to the A in the non-local scope. Okay, so naming blocks is kind of a convenient thing that you can do in Ada, and honestly, it's kind of cool, I suppose. Anyways, symbol table is kind of like a dictionary. It must support insertion, lookup, and deletion of names with associated attributes, presenting the bindings and declarations. So this is a data structure in the end, okay? It can expand or contract as much as you want it to. Just completely based on the program and what it's supposed to be dealing with. Okay. So the attributes of the symbol table itself, or the components, are the scopes, the symbols, and the attributes. Okay. Within each scope, you have multiple symbols, and each symbol has a number of attributes like the types, possibly the values, locations maybe. It depends on the implementation and how much you need to keep track of in order to do what you want to do. Okay. So the symbol table, well, what we've been discussing is kind of abstract even here, but the implementation can vary using like more basic data structures such as hash tables or search trees or arrays. In compiler design, we went with an array of like 100 elements or something. So that was one way to do it. We could have also gone with like some kind of stack or a linked list. It doesn't really matter. Point is, you can implement it however you like. Now, on entry into a block, all declarations of that block are processed and the corresponding bindings are added to the symbol table. Okay, so what's being done here is that you're assuming that all of the declarations are done at the start of the block, as is done in Ada, and then you go through all of those declarations at once, which are at the start, and you add them to the symbol table. And then once you reach the end of the block, as is the case here, you're going to remove all those declarations, so A and Y, okay? This process is called scope analysis. Now, when you exit, any kind of bindings that may have existed will be used, okay? So for example, with B2, once you exit, you're going to remove A from the symbol table and also B. And then after that point, the name A is going to refer to this A rather than this A one more time, okay? So let's consider the following C code, with which we saw a few slides earlier. The names in the program are X. Okay, Y wasn't there originally, but anyways, nor was Y. Array. Okay. So X, Y, P, X again, Y again, then Q, Y again, main, and X again. Okay. So you have multiple X's and Y's. Each of them is declared in a different scope. Now, obviously, if you declare twice in the same scope, that's going to be a problem, but within different scopes, it's totally fine. At this point, you have two things in the symbol table. The first thing is the binding between X and these attributes, int and global. and same thing but with y, character, and global. Okay. At this point, okay, you have the name of p, which is a void function, and what you've done here is kind of like pushed the new declaration of x, wx, into onto a kind of stack, and the top of the stack is the x that like is the thing that you're actually referring to when you say x. Okay, so when you say like x equals like 1, then the x that you're referring to is the top of the stack here, which is the double that is local to p. Okay, next. At line 7, you do the same thing. Top of the stack here for y becomes the int array that is local to the nested block in p. So again, we're just discussing this in the abstract, just like informally, the nested block in p. But if you're implementing this in a compiler or an interpreter, then you're gonna have to do something like the lexical addressing that we saw a few slides earlier, right? Now, at line 10, after the declaration of p, or definition, sorry, ends, this x and this y are removed from the symbol table because, well, they're local to the function p, right? So they're removed. But obviously, p itself is still there because you need to use it later, okay? So its binding is kept, but for x and y, we're back to the original declarations, original bindings. Now at line 13, you have void q, so q is now added to the symbol table as a void function, and you have the declaration of int y inside of q. So that's gonna get pushed off onto the stack for y, and that's gonna be an integer local to q. And at line 14, after q is ended, we're gonna pop it from the stack. So there is no more int y local to q. Now it's only the character that is global. Finally, at line 17, finally, at line 17, we're gonna have main, which is an int function, because clearly this is a C program. I hope. And character here, char x, is local to main, so this declaration causes it to be pushed onto the stack for x, and the top of the stack is this actual character, and below it is the local declaration. So when we use the name x later in the function main, we're going to be referring to the one at the top of the stack, which is this one, and not this one. Next, symbol table for statically scoped languages. What we discussed is a look at how the compiler processes the program and generates a symbol table prior to execution. So as the case of the symbol table is matched by the compiler and the bindings of the declarations are all static. Now, for dynamically scoped languages, declarations are processed as they are encountered along the execution path through the program. This results in a different scope rule, which is called dynamic scoping, and is used for functional languages like Lisp, where an interpreter is invoked rather than a compiler. So let's look at this now. C is statically scoped, but we're going to go through this as if it's dynamically scoped, okay? So we're going to start at the execution, the start of execution, which is, the main function. So that's where we start. We declare character x, and then we go into function q, right? So we have x is well, it has the global and it has the character that is local to main. We have the global character y equal to a. We have the void functions p and q and the main, right? Now, symbol table at line 17. This is what it looks like. For the global variables, they're always added at the start, at the bottom of the stack, let's say. And whenever we get to this function call, we're gonna jump over to here and we're gonna see this declaration. We're gonna add it to the symbol table, right? And then we're gonna execute this, and then we're gonna execute p, and then p in turn, we're gonna jump all the way to here eventually, yeah. So right here we have a new declaration of x, which is double x equals 2.5. That's gonna be the top of the stack. So whenever we say x, we mean the one local to p. And then going into this block, we're gonna have another thing here, another entry for y, which is that it's an integer array of size 10, local to the nested block in Q and in P, sorry, and so on. So that's just a rough look at it. Obviously, if with if this wasn't declared in P and we used X, then we'd be referring to this one, even though the top of the stack is this guy. So that doesn't really apply. You have to consider it a little differently. But anyways, the example demonstrates a serious problem with dynamic scoping since non-local variable references cannot be predicted prior to execution, neither can the data types of the variables. Luckily, in the previous examples, conversions were performed between character and int. However, this is not always possible. So dynamic scoping kind of has some problems in that it can be the case that incompatible data types are kind of operated on together, which can cause like some problems, obviously. And the idea here is that static scoping and type checking allows you to avoid these issues earlier, okay? Not during the actual execution of the program. But if it's done dynamically, then you're not going to be able to tell unless you actually test the program and go through all of that. So this is one advantage that static compiled languages have over interpreted languages. Local symbol tables. A struct declaration actually contains a local symbol table itself as an attribute. This local symbol table cannot be deleted unless the struct variable itself is deleted from the global symbol table of the program. So here we go. Suppose that we go through here and we declare the struct x, which has an integer, a character, and a double, and the integer is equal to 1, the character is equal to a, and the double is equal to 2.5, right? Now, this x here refers to a struct. And this struct is itself a symbol table, where inside of which the name a, so if you say x.a, that's going to refer to this guy, x.b is going to refer to this guy, and so on. So as you can see here, x.a, x.b, x.c. Similarly, with the y here, a struct of the same attributes, you're going to use y.a, y.b, and y.c. So that's its own symbol table. Okay? Local to y. Let's see. A more typical structure for the symbol table of the program is to have a table for each scope. When each new scope is entered during the parsing of a source program, a new symbol table for it is pushed onto a stack of symbol tables. Okay. Local symbol tables with nested blocks. Let's consider the following ADA code. So this is using some libraries, I guess. This is a procedure. The block starts with a couple of declarations and they're initialized. And then it has another procedure within it, it seems, which has a single declaration, which does that, and then starts with another block with a declaration and some code, and then there's more code. Okay, okay. That sounds like fun. So we start with EX, okay? Now in EX, within the scope of EX, we have X and Y, okay? So we have X and Y. And then we have the procedure P. So we add that here. Now the procedure P has a local X, and so we add that here. And then it has a block called A. And so we add A, which, since it's a block, has its own symbol table as one of the things in P. So A has its own symbol table, which is this guy. And in A, we have just Y as an element. Okay? And since this is the top of the stack, then whenever we see Y, that's going to refer to this guy, as long as we're within this point of the program. Okay? Moving on, the names declared in the scope are then entered in the symbol table. If a duplicate name is encountered at this point, then the name has already been declared in the same scope, and an error is returned. So if you declare the same things twice in the same scope, you're gonna get an error. Moving on. When a reference to a name is encountered, for example, the call to the put function. So where is it? Here. A search for it begins at the top of the stack. And if it's not found in the top of the stack, like the table that is at the top of the stack, then it's gonna go to the next table and the next one, until the bottom of the stack is reached. And if you still cannot find X, for example, then it must be that X hasn't been declared, and so it's gonna return an error. And that concludes this lecture on semantics in programming languages. I'll check the next two lectures and hopefully record those before it's way too late. I can't imagine how helpful this video will really be for the present semester, but that's fine, I hope. What can we do, man? Okay. Okay, let's move on to lecture 8, which is on data types. This lecture extends the discussion from the previous lecture, which was on semantics in general, as well as symbol tables. So, let's start. Data types, well, every program uses data in some way to perform the computations that it needs to perform. And the data is collected into data structures and manipulated by algorithms. Key thing is that data types, well, there's basic data types in the programming language. No matter what language this is always going to be the case. So you have integers, real numbers, usually represented by the floating point approximations to real numbers rather than the actual real numbers. You also have Boolean values and characters. Just a set of examples, okay? And then you also have mechanisms for constructing new data types from these. So for example, by having a data type that is comprised of two integers. Okay, we'll see some examples of those later in the lecture. Now, a data type has like a range of values that the value can have. But due to hardware limitations, or rather literal impossibility, there's always going to be an upper and lower bound for values, okay? So for example, on a 32-bit computer, a signed integer value can go between 2 billion and minus 2 billion. Rough number, I don't want to say the actual thing. It's roughly 2 billion and minus 2 billion, okay? And this is because in a single 32-bit computer word, you can't represent more than that many values. However, if you use multiple words and you have the algorithms to be able to deal with that, then yes, you can represent larger or smaller numbers. There's no issue with that. Okay? Now, data types, well, different languages deal with them differently. Some of them ask you to declare the data type explicitly whenever you declare a, or introduce a variable, okay? And this is needed because sometimes the programming languages need to be able to tell whether or not a certain computation is valid. For example, uh, if you're adding an integer to an array, that doesn't really make sense, does it? So with a with languages that ask you to declare the types beforehand, then they're going to be able to check whether or not you're able to add an integer to an array. And as they're compiling, for example, they're going to notice this error and let you know, hey, you're not allowed to do this. Fix it before you compile again, okay? But with other languages, this error is not going to be checked until it literally gets to that point in the execution of the program, at which point it's going to realize, hey, I don't have any way to deal with this. So I'm just going to crash the program or, throw an exception. So yeah, moving on. Scheme, which is a dialect of Lisp, and we've seen Common Lisp before in this course. It's a language with no explicit types and no translation time typing. While Ada, which we saw in the previous lecture, is a very strictly typed language and performs strict type checking. Okay. These are just some advantages of static type checking. Allows you to allocate memory more efficiently, reduces the amount of code that you need to compile, improves both the writability and the readability of the code, improves the security and reliability of the code, removes any ambiguities there might be, and can be used to prove the correctness of the program. Now, a data type being a set of values is not sufficient to define what a data type is. Besides the set of values, you also need to have a set of operations that can be done on those values, and those operations need to have special properties. Okay. So, for example, with the integer data type, the set of values is, the integers from, let's say, -2 billion to +2 billion. And then the operations are plus, minus, times, divide, and so on, as defined by the computer's processing unit, okay? Now, type checking is the process a translator goes through to determine whether the type information in a program is consistent. So whether you're using, let's say, a variable according to what type the variable has, right? So if you're using a variable as an integer, for example, as a character, that doesn't really make sense, does it? Anyways, an example of type checking could be that with this statement, x equals y plus z, can the type of the result of y plus z be stored in y? So the result of y plus z, can you put it into x? Is there is the procedure for doing this well defined in the programming language, or are the types incompatible? Okay. Also, the type of y and z depends on the type of y plus z depends on the type of y and z. Okay. Also, the type of y plus z, actually determining it might not be the same type depending on what operation that is and what the types are. This is called type inference. Moving on, we saw earlier that we can construct more complex user-defined types from simpler data types. For example, we can define arrays out of integers. So 10 arrays, 10 integers. That's an example of an array. And this is a compound data type, sort of. Same thing in Ada. You can have 10 integers. And also you can give names to data types sometimes. So for example, type def int array of 10 integers with 10 elements. This is referring to the definition of a new type where the name array of 10 integers means an array of 10 integers, right? So you can just directly say array of 10 integers A, and then A will be referring to a new array that has 10 integers, okay? Same thing in Ada. You declare a new type called array of 10 integers, and you define it to be an array from 1 to 10, so with 10 indices of integers. And then you declare A to be an instance of this data type, okay? But the problem is during type checking, a translator must often compare two types to determine whether or not they are the same type, okay? So for example, these two should be equivalent. And the translator needs to be able in some way to determine whether this thing is the same as this, or like what does this mean in the first place, okay? And the way to do that is using something called rule equivalence algorithms, okay? Moving on, different types of typed languages. You have strongly typed languages, where the programming language definition specifies a complete type system that can be applied statically, and it guarantees that all unintentional data corrupting errors in a program will be detected at the earliest point. So any kind of uh, errors that would arise from you not handling the types properly can be detected very early with these strongly typed languages. Okay, then yeah, all of these type errors are going to be detected at compile time, with the exception of very few errors. So for the most part, everything's going to be checked. Okay. So all these different languages are gonna gonna kind of force you to define all the different types and how they might interact. Okay. Any compound or more complex data types need to be defined, and this can give you more of a, let's say, burden when you're programming in these languages. So these languages are very safe in a sense, but they're also annoying to use, so you should not use them and instead use an unsafe language such as C, just because it's easier. Ignore that part. Anyways, strongly typed languages, there's a few examples here. First one is Ada, a very, very strongly typed language. ML and Pascal, and C. For C, it's considered to be weakly typed because it doesn't check this stuff as seriously, kind of. Now, with untyped languages, also known as dynamically typed languages, these ones do not check the types during compile time, and are just gonna throw errors as they encounter the type errors during execution, okay? So dialects of Lisp, Smalltalk, and scripting languages such as Perl or Python, as you might have seen before, okay? So an untyped language does not necessarily allow programs to corrupt data. Rather, all the safety checking is performed at execution time. So it's not gonna check things as soon as possible. Rather, it's only gonna find these errors when it gets to that point in the execution. And this might be too late in some cases. So yeah, moving on. Type construction. How do we actually define more complex data type? We saw earlier the array of 10 integers example, but there's a whole science to this and to data types in general, type theory. So this is kind of a big area in reality, but we'll cover just like basic stuff. We have the Cartesian product, union, subsets, arrays and functions, sequences and lists, recursive types, and we need to keep in mind that types should not overlap, although that will be explained a little later, so don't worry about it for now. First, the Cartesian product, which is just a combination of multiple types. For example, the structs that we saw in C, okay? And this is a combination of an integer, a character, and a double, just as an example, okay? It can be multiple integers or an integer and like an array or whatever, just a struct. So this struct type has 3 different sub kind of components, and you can access them separately, okay? Then you have unions, which rather than being all of these at once together, you only have a single one of them. So this union, int or real, is either an integer or a double, okay? You can only use one of these at a time. You might end up seeing unions in the compiler design course if you've not taken that yet, so keep those in mind. Anyways, subsets. A new type may be a subrange of another type. An example, subtype integer type is integer range 0 to 9. Now, integers, as we know, like I'm just gonna speculate a little on what Ada does, is that let's say integers are 32 bits or whatever, and then this is just restricting the int digit type to only have values between 0 and 9. So it's not allowed to have like 2,147,000,000 something, right? Okay. Arrays and functions are also kind of types in a sense. So you can define arrays in most programming languages as a homogeneous collection of a single type. And functions can be defined as types as well, I guess. Sequences are like arrays, except they are potentially infinite. For example, streams and linked lists. So arrays, you know, they have a finite number of elements, but linked lists can expand infinitely, provided you have enough memory for it. Anyways, recursive types. For example, what you saw with the linked lists in data structures and algorithms is that each node has inside of it another node, except in this sense it's actually a pointer to a node or equivalent. I'm not gonna bother with this. Type checking. We saw more or less what this is about, but let's just read it. If type information is maintained and checked at runtime, then that's dynamic type checking. And it's done by interpreters. Now, compilers also generate code that maintains type attributes during runtime in the table. But dynamic type checking is only really required when the types can only be determined at runtime, and you can't do that before runtime, okay? Now, static type checking, the types are determined from the text of the program rather than the result of the execution and the like the environment or the inputs or whatever, okay? And it's done, yeah, before the execution. So it's all static based on whatever the programs actually, you know, contains, right? Okay. Strongly typed language must report all type errors as compilation errors. A language definition may not specify whether static or dynamic type checking is to be used. Type compatibility. Two different types may be combined correctly in some ways. They are called compatible. For example, int and short. Now, both of these are integers, but one of them is 32 bits and the other one is 16 bits. So you can add them together and put the result in like a 32-bit integer. That's totally fine. Similarly, you can just assign an integer to a short value So for example, short x equals 5 and then int y equals x, that's totally valid. Implicit types, sometimes they're implicitly inferred. For example, 2 plus y, 2 plus y, 2 plus 3, this gives you 5, which based on these two being integers is inferred to be an integer. And similarly for this one, however, if one of these is a double, then the result is going to be double. So it's inferred based on the actual types of the like the operands in the operation. Okay. And C, the following is an implicit int variable. Okay, I've never seen that actually, but that's kind of cool. Also in C, if functions have no return type indicated, they implicitly return an int. I've also, okay, well, in the previous lecture we had main that didn't have int in it, so I guess this is an example of that. Okay. Now, overlapping that we mentioned, it is sometimes difficult to avoid overlapping of various types. In Java, the following types overlap: int, short, long, byte, because I suppose they all count as integers, just of different lengths. Moving on to overloaded operators. The plus operator may be applied to any combination of int, short, byte, double, float, long. So you can combine this in any way. Float with int, that's totally valid, and so on. The thing is, this can be overloaded, this plus operator, because you can add strings together in this way inside of the println function. So the overloading here refers to possible different meanings of the same operator, okay? And this can be kind of weird because you might not be sure how to interpret something. If you aren't sure of the data types involved and so on, C++ sometimes has a problem with this because even though plus and plus might be intuitive, um, like adding two things might be intuitive. Like, what do you mean by adding things exactly? It completely depends on the types, and so you might need to check the definition of the plus that was defined for those specific types. Okay. Okay, type conversions. This should be the last part of the lecture. Usually you will need to convert from one type to another, and this can be implicit or explicit. So an implicit one is if you, for example, have an integer x and you assign to it a double value or a floating point value. Now this is going to just convert the 3.3 into a 3 and assign it to x, okay? Another thing is that in Java here, implicit type conversion, 2 plus 3, this is 5, but even though it's an integer, it's going to be converted to a double in order to be stored in this double x. And implicit conversions are also called as coercions. And they can be, type conversions can be widening or narrowing, okay? And this depends on the data types. So when you're converting from a type that has a wider range of values to a type that has a smaller range of values, then that's a narrowing conversion. If you're going the other way around, then that's a widening conversion. Now, explicit conversions are those where you explicitly say, hey, convert this into a double for me. So x here is an integer. You use this thing, double in parentheses, and that's going to convert it explicitly into a double. Okay? Now let's check here for a second. Most statically typed languages require that explicit type information be given for all names in each declaration. Okay? So, you know, with programming languages such as C or Ada and so on, every declaration needs to have the type information with it. It's possible to use an extension of type inference to determine the types of names in a declaration without explicitly giving those types. The translator can collect information on uses of a name and infer from the set of all uses a probable type for which all uses are correct. The Hindley-Milner type checking provides this kind of inference and is a major feature of strongly typed languages, functional languages such as ML and Haskell. So this is kind of a more mathematical thing and is, well, the details of it are outside the scope of the course, so you don't need to worry about it too much. And yeah, that concludes this lecture on data types. Uh, 7 p.m. already. I'll start with the lecture 9 in a bit. Who knows when this will be uploaded. Okay, so moving on to the final lecture on expressions and statements, selections, loops, and exceptions. The lecture here is going to be kind of an overview of some of the control structures in programming languages and what they look like based on things that we've seen in the previous lectures. So let's start with selection, which is if and else statements. You already know what these do. They let you choose kind of a branching where if a certain condition is met, then one of the branches is going to be taken and certain codes are going to be executed. And if that condition is not met, then some other code is going to be executed. And the way that the condition is done is using a Boolean expression, which evaluates either to true or false. We have some of the operators used for these comparisons. So yeah, true and false are literal values, just like numbers like 10 or whatever. Now in Java, you have multiple types of selection statements. You have one-way or two-way if-else statements, nested if statements, multi-way if statements, switch statements, and conditional expressions. But in the end, of course, you already know most of this, so I'm just gonna really quickly go over it. So the first one is one-way, in which if the condition is met, something's gonna be executed. Otherwise, well, there's no alternative action. Okay. So if true, it's gonna execute this and continue. If false, it's just gonna continue directly without executing the statement or statements. Okay. Yeah. If you're only gonna have a single statement being executed, you can leave out the braces. So there's no braces here because you don't need them. It's only a single statement. But well, it's usually better practice to have the braces anyway. But that's not related to the lecture here. Couple of examples, I guess. Now the two-way if-else statement. This is when you have an alternative action that you would want to be taken if the condition is false. In that case, you put an else here and a block, just like that, and you put whatever statements you want to be executed in that case. And this is the flowchart or diagram for it. Next is nested if statements, in which an if statement can be inside of another if statement. Simple enough, I suppose. And the else here is following this outer if rather than the inner one. Okay. So that's something to keep in mind. But if you had omitted the braces, then if you remember the grammar in lecture 6 that had the if and else, well, the usual rule is that the else is following the most recent if. Okay. So if you don't want that to happen, you'll need to put braces to resolve the ambiguity. Anyways, nested if statements can be used to implement multiple alternatives. And here's an example. So as you can see here, the else elf is following this if, and this one's following this one, this one's following this one, and so on. Anyways, so this is the an example of using if statements to represent multiple different branches. All of these different branches, ways that these things can proceed, right? Okay. You can also just say as if directly instead of formatting it in this way. Okay. It's kind of more, a little more concise and also easier to understand. So yeah. The logical operators are the ones that you use to actually form the Boolean expressions that are used to determine whether or not the condition is true. And the ones you like more compound expressions, things like not and or and XOR, right? So this is true if the thing following it is false. This one's true if the things to its left and right are true, both true. This one's true if at least one of them is true, and this one's, well, if the ones to its if the expressions to its left and right are different in Boolean value. So here's the truth tables, and then we have the switch statement, which take a single expression and evaluate it, and based on its value, they're going to determine a course of action to be taken. Okay, so if the switch expression, let's say, has the value 2, that's going to go to here and execute this part, and then when it sees the break, it's gonna exit the switch statement entirely. Okay, so the break kind of takes you to after the closing brace here of the switch statement. The switch expression must yield a value of character, byte, short, int, or string type in Java, and must always be enclosed in parentheses. The values must be constant, so value 1, value 2, value n, and so on. These all must be constant and have the same data type as the value of the switch expression. When the value matches the switch expression, you're gonna go to that case and you start executing the code until you encounter a break statement or you reach the end of the switch. Okay. So for instance, if you remove this break and then the switch expression evaluates to value 1, you're gonna execute this, and then you're gonna execute this. This is called fall through, if I'm not mistaken. And then you're gonna see the break, and then you're gonna jump to the end. Okay. And if the value in the switch statement is not one of the cases, then you're gonna go to the default case. It's optional, by the way. So if you don't want it, then when there's no matching values, it's just gonna skip past. Okay. Right. Here's an example. Another one. Conditional expressions. I think this is the last one. So you have an expression here, followed by a question mark, and then two possible values. Okay. It's gonna return expression 1. So this entire thing will return expression 1 if the Boolean expression is true. Otherwise, it's gonna return expression 2, which is after the colon over here, if the Boolean expression is false. Okay, this is a common one. Max is num1 greater than num2, question mark. If yes, if this is true, then it's gonna return num1, otherwise it's gonna return num2. Okay. Same with checking even or odd. If the modulo 2 is equal to 0, then that's even, otherwise it's odd. Then we have loops, which have, repetition. While loops have a condition, and it checks the condition at the start of the loop. If it's true, it's going to execute the loop body and then check the condition again. And then if it's true, it's going to, execute the body again, and so on. Once it's false, it's going to jump to here after the closing brace. So here's a flow chart. You start here, you check the condition. If it's false, you're going to go after the loop. If it's true, you're going to execute and then go back and check the condition again. Okay, and this is just an example of that. Part of the loop that contains the statements is called the loop body. One-time execution is referred to as an iteration or repetition. Okay, we don't need to see all that. Counter controlled loop. Now, sometimes you want to uh, use a while loop to loop a specific number of times, let's say 100, in which case you're going to declare something like a counter, initialize it to whatever you want, and you're going to increment it every time the loop, you know, executes until the condition is met. And there's a shorthand for this kind of loop, and that's the for loop. So it's a concise syntax for counter-controlled loops, okay? So rather than this, you can just write this, right? Keep going. So initial action, which is before the first semicolon. You can do whatever you want here, believe me. Like you can declare multiple variables if you want. Then you have the condition. If it's false, you can skip past. If it's true, then it's going to execute the body and then perform the action that's after each iteration, which is after the second semicolon, okay? And then it's going to go back to here and check the condition again, okay? Right. Nested loops, same idea. You just have a loop inside of another loop. So as an example, okay, it's split into two, so I'm not gonna bother. Never mind. Okay. Exceptions in Java are objects which are defined using classes. The root class for exceptions is called throwable. Okay. So obviously in Java everything is inheriting from object. So that's why you have that on the left here. But anyways, throwable, there's two types, exceptions and errors. So you have all sorts of exceptions on here. It doesn't really matter. Point is, when an exception is thrown for whatever reason, if it's inside of a try-catch block, for example, this structure, so you're gonna put try, and then within the try block, you're gonna put multiple statements. The statements, if they run into some problem, they're gonna throw an exception, right? And depending on what exception is thrown, you're gonna have multiple catch statements that can, you know, catch one of those exceptions and handle them and execute some different thing just to like keep the program, let's say, under control, or like prevent it from crashing and just put it in a state that can that's functioning normally instead of like crashing or causing some kind of weird errors or whatever. I'm speaking vaguely here. Anyways, a compile error will result if a catch block for a superclass type appears before a catch block for a subclass type. So runtime exception is a subclass sub kind of thing that inherits from exception, okay? And what happens here is that if something throws a runtime exception, this is going to be the first catch, and runtime exception is a type of exception, so it's going to be caught by this one. And that's obviously not what you want to do, what you want to happen. You want it to be caught by runtime exception here, okay? Which is the specific, you know, handler for this type of exception. So that's why you need to put it before that. Now, if you don't do that and you put it in the wrong order, it's gonna give you a compile error. So yeah. Here's an example of an arithmetic exception happening where, let's say, you divide by 2. So it takes inputs from the user, and if number 2 ends up being 0, and after the division, it's going to throw the exception. Because of this division, it's going to go over here to the catch block that's corresponding to the arithmetic exception and, you know, handle it. Tell you that, hey, you cannot divide by 0. and then continue the execution to maybe ask the user again for two numbers or whatever, depending on what the program wants to do, or the programmer rather. As the name suggests, to throw an exception is to pass the exception from one place to another. Okay, that's the explanation for the actual code, so we don't need to cover that. This is the general format. This is the same idea, except it's input mismatch. If you, for example, input like this is expecting an integer, but you input a double, as you can see here. Okay. Exception types, here's a few of them. I don't think this matters too much for the final, if at all. But yeah, class not found, IO exception, arithmetic exception, null pointer, index out of bounds, illegal argument, whatever, just read that if you want, but it doesn't really matter. I think that's the end of the lecture. Yep. And that should conclude the entire final exam review. Now, there was the object-oriented programming lecture, if I'm not mistaken. A certain individual from class told me that it's coming in the exam, but you should just review, like, if you want a review for that, you can just check the reviews on the channel for the actual object-oriented programming course rather than this one, because that's going to cover everything in more detail. And besides, you should know this anyway. It's like covered 2 courses ago, right? So yeah, that's gonna be the end of it for this lecture review. I'm not gonna bother with the samples. Just solve those yourself if you want. Maybe ask on the groups if you need to. And yeah, that's it. Goodbye, and thanks for watching. Like and subscribe.